So how does that arise? Well, he asked me if the result was no. If so, where could it be found? And if not, could I supply a proof? And this came in an email when I was actually visiting Angela Hamel in Waterloo, and she reminded me almost immediately of a theorem of MacDonald, which says if you do look at the same object, but you don't restrict the number of rows, but you restrict the number of columns of your Young diagram, this lambda prime is the conjugate that Joris is explained here, then you can express this sum as a determinant. So that's already in the literature since 79, and this is the new conjecture, and they don't look very much alike, but on this left-hand side is a very simple conjugacy rule that maps you from one to the other. So the question is, can you derive one from the other? And you can, and I'll try and convince you of that. So what's the strategy? We'll want to recast, McDonald's formula comes in the form of a determinant. Can we recast that in terms of Schur functions? Then can we use this conjugacy? As we can see on the left-hand side, that's all we need, is some conjugacy operation. So, and then having done that, to recover this formula, can we somehow see in a more fundamental way why these row length restrictions come in one case and column length restrictions in the other? What's the origin of this restriction? So first, I'll give you some preliminaries on Schur functions and Schur function series partitions and so on. So this is background information. But I want to discuss some determinant identities, which will be the key to the proof of the conjecture. So, Schur function. N is a fixed positive integer, x is a sequence of indeterminates, lambda is a partition, these are all non-negative integers, the parts of this partition. The weight is the sum of those parts, the length is the number of these parts which are non-zero. Then the Schur function, we all have different ways of defining a Schur function, but one way to define it is a ratio of two alternates in these variables x1 to xn, so numerator and denominator are separately antisymmetric, and the interchanges of rows, interchanges of the x's, so the quotient is symmetric, so it's a symmetric function, and the denominator is the famous Van der Waals determinant. So that's one way of defining Schur functions, and their importance lies in the fact they form an integral basis of the ring of polynomial symmetric functions. And from our point of view, one other constraint that's really important is that if n is limited and the length gets too long, L lambda is greater than n, this Schur function vanishes. So that's an important constraint. Partitions and Young diagrams, you've seen some of this thanks to Joris already. A Young diagram consists of boxes, mod-bounded boxes arranged in rows, whose row lengths are determined by the parts of the partition. The conjugate partition determines the column lengths, or is determined by the column lengths. And Frobenius notation is just a notation in which you specify exactly the same object, the same partition, by means of arm lengths and leg lengths with respect to the main diagonal, and the length of that main diagonal is sometimes called the rank of the partition are boxes on this main diagonal, and these numbers specify that partition equally well. So this, you can represent it this way, they're all equivalent representations. Okay. Special families we need, let P be the set of all partitions including 0. I always include 0 in the set of partitions, so it's the empty partition, all the parts are 0. The unique partition of weight, length and rank 0. Then for any integer t, let pt be the set of partitions which in Frobenius notation have an arm length and leg length corresponding ak and bk differing by t. And t can be positive, negative or 0, but some integer for all k and all r, including 0. So one important thing is that the 0 partition belongs to these sets for all integer t. And one special case which we met in Popov's talk is when t is 0, these arm and leg lengths are the same, the partition is conjugate. It's symmetric under reflection through this main diagonal. So the self-conjugate partitions correspond to P0. Okay, Schur function series. This is the generating function I've already given you. This is the 1 over factor in the Joris conjecture formula. It generates all the Schur functions. There's lambda, all lambda in P. The inverse of this is what we meant in Popov's talk. Lambda is in P0, and we have a weighting factor here if we choose these signs minus and minus for this integer. So those are well-known classical results. the first series, these are rather different though. The first series is infinite. It's 1 over. You formally expand each of these terms in a geometric group. So this is infinite. This is finite. The length is restricted by n. Here the length of lambda and the length of lambda prime are both restricted in this second case, less than or equal to n. And the second series is the one that's the denominator of the conjecture. The determinant identities also go back a long time to Littlewood in 1940, and here they are. For lambda in P0, lambda in P1, lambda in P of minus 1, these are the generating functions as determinants. And so that provides the possibility of linking the determinantal expression of Macdonald with some generating function for Schur function series. These determinants are all n by n, and the strange notation that appears here, this is the truth function. If j is greater than 1, this is 1. But if j is equal to 1, we just have this one term here, this one disappears. So these are the generating functions. And I want to generalize that formula. Those formulas, that's what I need, a generalization of those results over here. But before doing that, let me see that it's somehow relevant. This is Macdonald's theorem. The lambda prime is restricted in length, so the first row cannot be too long. This is the determinant expression. We can rewrite it. We just change the ordering of the columns and change sign. Then we can use Littlewood's determinant identity on this bottom part to use this fellow. And then we can use Littlewood's generating function to deal with the other part of Macdonald's formula. And we rewrite it in this form. And that's looking much more like the LSB conjecture. The numerator is still a denominator. So we want to write that, sorry, the numerator. The numerator is still a determinant, and we'd like to write that in terms of Schur functions to make the connection with the LSB conjecture. How are we going to do that? Well, we need a number of results, including some modification rules. Kappa here is not necessarily a partition. This is just a sequence in which the kappa i's, the components, are integers, positive, negative, or 0. You can still define a Schur function with respect to those labels, and it's given by the same formula, with these kappas just no longer all positive and arranged in order. And then every one of these is either 0 or it's a multiple of a Schur function specified by a partition label, except for a possible factor of the product of all the x's to some power. It's fairly easy to see that, to establish that by just looking at the determinant. If you commute the columns, you get some strange identities. If you interchange the j and the j plus 1 column, then s kappa of x is minus s mu of x, where with this interchange you decrease this label on the left by 1 and increase this by 1. And if you repeat that, you can slide the kappa j plus 1 component of this partition, this non-partition label, to the left, and you add a number of 1s to what's left here. And that's sort of what happens. So we have a trivial modification to apply if kappa is not itself a partition. So here's a simple example. If n is 4, kappa is 0, 4, 0, 9, then this is equivalent to s lambda of x with lambda equals to 6, 4, 2, 1. And it's trivial to see. If you write the left-hand side down, this is what you get. You add 0. This is the van der Waals thing. I've just written down the elements in one row. You add 0, you add 4, you add 0, you add 9. And then you just reorder that in standard order. You just commute the columns here, and you get the determinant corresponding to 9 minus 3 is 6, 6 minus 2 is 4, 3 minus 1 is 2, and so on. So it's trivial to do this, absolutely trivial. Or you can proceed iteratively using the identities I just given you. Okay. Diagrammatically, what this corresponds to doing is taking a non-regular diagram and regularizing it somehow. And the rules are, you push this one past these 3 slots and increase the length of those slots by 1, and you shorten the top one by 3. And then you do the same, you push this one past this, you decrease its length by 1 and add 1. So you get this diagram. So it's a trivial geometric type operation. And you can see it another way. You can wrap, instead of taking this as a horizontal line, you can somehow make it itself regular by just wrapping it vertically along, and then wrapping this one round it. And then if you slide this through here, you get the shape. It's another thing doing exactly the same thing. But in both cases, we find that we arrive at this partition label 6421, which has this Frobenius notation, 5321. Okay, well let's look at this in a more general situation. Let kappa j be 0 unless j takes on certain values. So it's certainly non-balanced. Maybe a lot of zeros. And then you can order these so without loss of generality, b1 greater than b2, br greater. And then let kappa j be this number if j is bk plus 1. So that kappa has this form. So just another way of writing your original and specifying this arbitrary looking kappa. So it may have zeros, umpteen of them, and you may have these factors. If after you've done that, these coefficients a1, a2, ar satisfy this condition, that's the condition for an arm length condition on Frobenius notation for a partition, then this f kappa x is a sign factor, signature factor times this partition, where the a's and the b's I've got in this formalism are the arm and length, arm and row length of this partition. This is an example. Kappa is 0, 4, 0, 9. Kappa is 0 unless j is 2 and 4, second and fourth position. That makes the b's 3 and 1. You just add and subtract 1 from each of these. The rank is 2. You can then put in the k's and you find a1 is 5, so on the whole, and you do get this partition with arm length 5, 2, column length, arm length 5, 2, leg length 3, 1, and it corresponds exactly to what we've done before. We move from this non-standard 0, 4, 0, 9 to this standard partition with the arm and leg lengths labeled. Okay. Well, with that in mind, then the lemma that generalizes all those identities of Steppenwood is this one. This determinant over this one with a parameter q and a truth factor, so this plays a role if you're in a column number with a column number greater than minus t. T itself remember to be positive, negative, or 0. Then the claim is that this generates all partition Schur functions labeled by partition in the set pt. And we have this sign factor, which is a generalization of what appeared before, where t is any integer q is arbitrary. So that's the lemma. And the special cases, these three special cases are little bits results. Okay, you can prove it algebraically. I won't go through it. It's a combinatorial, bijective type proof, but you can prove it algebraically as well. And it just does everything that I said explicitly in terms of shifting those rows around and bending them, and you get exactly the right factor. So I won't go through this proof, but it's a one-page proof. That is the proof. In the example, n is 4, t is 2. This is this determinant. Here it goes. We expand. That's what we get. These are the columns labeled explicitly. You expand that in terms of Schur functions labeled by non-standard sequences. You standardize them, and this is the answer. And it all looks a bit obscure at this level. Remember, n is 4 and t is 2 in this case. And you find when you've done it that you get this sequence, which in Frobenius notation is absolutely trivial. You get all the these are all the rank 1 partitions to be with the difference between the arm length and leg length of 2. And then you combine those in all possible ways. And all you have to do is look at the sign factor. So that's the determinant.